Good morning, everybody. I would like to take you on a journey through the world of the fusion fuel cycle and through the world of deuterium and tritium. And in order to do that, I thought I would introduce you into the what is called inner and outer fuel cycle of fusion reactors, then go to properties and usage of tritium and deuterium, dwell a little bit on production, inventory, tritium in science and technology, before coming to handling of deuterium and tritium, confinement, the fuel cycle of ITER, environmental aspects, and then a summary. Well, those of you who attended the first lectures, or in general, I'm sure will know that the sun fuses hydrogen to helium in a simplified reaction scheme. It's hydrogen fusing to helium, a positron, a neutrino, and of course there is net energy coming out of the reaction. Well, ITER is not using hydrogen, but will employ deuterium and tritium, which are both hydrogen isotopes. Deuterium and tritium are fusing to helium, and there is a neutron as well being produced. The overall energy is 17.6 MeV, mega electron volt. So why not simple hydrogen, but deuterium and tritium? Well, this is because technically, because of confinement and other aspects, the reaction between deuterium and tritium is the most suitable fusion reaction. As I said, there is helium produced and there is a neutron, and they both carry the total energy released by the reaction. If you want so, you may consider helium as the fusion product, as the ash of the burning reaction, if you compare that with a real fire. Well, you all know that the plasma is confined in the shape of a torus, and there is deuterium and tritium supplied to the plasma chamber. Only a small fraction of the deuterium and tritium supplied is really burned by the plasma. The helium produced would lead to a radiation loss of the plasma, and that would sooner or later stop the plasma from burning. So we need to remove helium plus the unburned DT with pumps and give it into kind of black box where helium is removed and the deuterium and tritium unburned being recycled. Of course, what has been consumed, the deuterium, need to be added. You need to top up what has been burned. And deuterium can be extracted from natural water. There is what is called standard mean ocean water, which contains 0.016% of deuterium in hydrogen. When it comes to tritium, we need what is referred to as being the outer fuel cycle. You see here there is a breeding blanket containing lithium, and this lithium comes from salts or minerals. And the neutron from the fusion reaction, or the DT fusion reaction, hits the lithium atom, and thereby tritium is produced from these two lithium atoms. The tritium is extracted through purge loop, for example. Here there is a removal and recovery system, and this tritium then is introduced from the outer into the inner fuel cycle, and this makes the fusion reactor self-sufficient as far as supply is concerned. It's very important to note, ITER will not have a full breeding blanket. ITER will test the technology, but as far as the tritium consumption is concerned, ITER will need to import tritium, and this will come from what is called can do fission reactors, heavy water, natural uranium moderated reactors. I have a picture here of such a reactor. It's a Darlington site in Ontario in Canada. About 100 grams of tritium is unavoidably produced in such reactors per operational year. We have something like 40 reactors being operated in the world, about 15 in Canada, about 15 in India, there are 4 in Korea, there's at least one in Romania and in other countries. So tritium for ITER can be made available through these reactors, which for them is a waste product. I want you to compare, however, the 100 gram produced here with the 56 kilogram of tritium required per gigawatt year of fusion power. It says that a real fusion reactor would indeed need a breeding blanket and would indeed need to breed its own tritium. Well, when it comes to ITER and deuterium and tritium, it is very important to mention that ITER is the first fusion machine fully designed for operation with deuterium and tritium. And this is why ITER is a nuclear facility. Even if ITER would not produce neutrons, even if there would be no activation, just because of the amount of tritium ITER is handling, it is a nuclear facility. You see here an artist view of the ITER site. This here is the tritium plant building. I think the artist knew how important the tritium plant is. That's why he almost did put it in the middle of the picture. Employing DT means alpha heating of the plasma, means that the fusion reaction provides energy. This is what we are all after. Of course, it also means that we have to have processing systems for tritium, we have to have auxiliary systems which are necessary for the safe handling of the material. And I will introduce you into the barrier concept, multiple barriers to confine deuterium and tritium in its process components. Some background as far as history, as far as usage of tritium is concerned. It was about 80 years ago that Urey discovered deuterium, and only 3 years later Paul Hartwig and others synthesized tritium for the first time. And what they did at that time, they fused deuterium together to make tritium, a reaction, by the way, which will also take place in the ITER plasma chamber. It will be a reaction which will take place once ITER will use deuterium. Well, tritium is used in many areas of science, in medicine, as a tracer, as a light source. Some of you may even have watches illuminated by little tritium sources. They're still on the market, even though former design was such that tritium was leaking out and caused even a measurable dose to those who would use these watches. There is tritium in Earth, atmosphere. There is no tritium in space. Tritium is continuously produced in the upper Earth atmosphere through the reaction of nitrogen with cosmic neutrons. And this way, we have 200 grams of tritium per year in the atmosphere of the Earth. Because of 200 grams tritium per year, the inventory turns out, under steady-state conditions, to be 4 kilograms. There is, however, a residual inventory from nuclear weapons test in the late 60s, beginning of the 70s, and the residual inventory here is about 40 kilograms. This is continued to decay until a new steady state is reached. Most of the deuterium in the universe was formed about 10 minutes after the Big Bang. Whatever was there as far as tritium is concerned has disappeared. There is no tritium in space, as I said. So if you ever hear in a newspaper an article saying there was tritium in space observed, it means that likely that an alien spaceship or so with a leaky fuel reactor just passed by Mother Earth. So there was no tritium in space. You may go to the movies, even though action might not be your genre. There was a movie, Spider-Man 2, and in this movie, Dr. Octopus built a fusion reactor, and with this fusion reactor he almost destroyed New York City. He knew that he would need tritium, and tritium is a rare material, hard to get, so he was really after getting tritium, and said that, well, you know, there was only 12 kilograms available on this planet. Hollywood is fiction, the number is wrong. Today's tritium is 20 kilograms and not 12. However, it is not unlikely that ITER will almost completely consume the available tritium from CANDU reactors, will consume all the waste, as far as this is concerned, from fission reactors. To introduce you into the properties, well, deuterium and tritium are both hydrogen isotopes. There are no other isotopes of chemical elements which have their own dedicated names, symbols, D and T for deuterium and tritium. Tritium is the heaviest hydrogen isotope and is radioactive. Well, it's radioactive and it's a pure beta emitter, which means there is no alpha and no gamma radiation either. It's just the electron, which comes out in an antineutrino. I will talk about this antineutrino in a moment a little bit more. Half-life is 12 years, very short. Because it's very short, any waste containing tritium is not of concern for a very long period of time. 100 years, foreseeable time scale for all of us, is the time required to have the tritium disappearing just because of the decay. Because of decay, about 50 grams is lost at an inventory of 1 kilogram. And this is, you know, somehow the inventory of the ITER fuel cycle. So even though there is no burning of deuterium and tritium, 50 grams of tritium would disappear in ITER. 1 gram tritium is about 3, almost 4 liters. I think the US would say it's a gallon, nearly a gallon of volume. There is 300 milliwatt of decay heat being produced. You may compare that with a light bulb. It's about 1% of the heat produced in a light bulb. Because of the short half-life, the activity figures for tritium are high. It's 9,600 curies, or 3.5 times 10⁻14 becquerel per gram of tritium. It's very important to mention that the energy of the beta is coming out of the tritium decay is very, very low. Tritium is the energetically weakest natural beta emitter. In case there are nuclear physicists here need to mention that there is another isotope, but this is practically stable, so I neglect that when saying, let's see, energetically weak, as I saw Pierre being concerned about the statement. Well, because of that energy, shielding of the tritium radiation is not an issue. Simple paper will shield completely the electrons coming out of the tritium beta decay. The maximum range in air is about 6 millimeter. In solids, metals, it's less than 1 micrometer. Of course, we need to strictly avoid any inhalation or ingestion of tritium, because there is the risks. For experts among you, tritium has the largest known gyromagnetic ratio, which makes it very sensitive for nuclear magnetic resonance spectroscopy investigations, and because of the spin, there are spin isomers, but I don't want to dwell on that. But rather go to why tritium is interested for those who look into particle physics research and cosmology. Well, I did mention there's an electron, there's an antineutrino, and people are interested in the masses of these elementary particles, the mass of the neutrino. All neutrino masses so far are unknown, and this is a significant lack of know-how in the standard model of physics. And if we would do spectroscopy, if we believe in conservation of mass and momentum, we could measure the neutrino mass through high-resolution spectroscopy of the tritium decay electrons. And this is exactly what people did in the past, what people do today. Non-neutrino masses would disclose themselves in the spectra of the tritium decay. So if we would know the neutrino mass, we would know more about their contribution to dark matter. Because at this moment in time, we observe only a small part of the universe content of material. Why could they contribute? Because we have 1 billion more neutrinos in the universe than atoms. There are something like 340 neutrinos per every cubic centimeter in the universe, and also right here. And right here, we have 65 billion solar neutrinos per square centimeter per second. Square centimeter, that's the thumbnail. 65 billions penetrating us. Fortunately enough, they don't interact. They do, however, show what is called oscillation. It's unlikely that they do it while in your body, so you won't feel any shivering or so. Handling of deuterium and tritium involves techniques which are typical for gas processing, because hydrogen isotopes are gaseous under normal conditions. They are colorless, odorless, tasteless. Nobody tasted tritium, so that's why I excluded it here. Well, even though they are gaseous under normal conditions, pellet injection will use solid deuterium and tritium. We'll use deuterium and tritium ice. I will tell you more about that in a moment. And the tritium plant isotope separation system distills liquid hydrogen. So we are handling not only gases but also solid and liquid tritium. Everything in ITER which comes into contact with tritium must be tritium compatible. What does it mean? Well, it must be leak tight above all, because of course we don't want to have the tritium and deuterium leaking out for both economical reasons, for ecological reasons. We don't want to have this being trapped, because it would mean it no longer be available for the machine. We prefer only metals or ceramics in direct contact with tritium, because organic materials will degrade, and the standards are described in the ITER tritium manual. Well, there is one property of hydrogen isotopes which is very important for us, which is movement of tritium in solids. Hydrogen atoms move very quick. As an example here, you see hydrogen atoms occupying gaps in a crystal lattice, and they're not sitting there still, they move. They jump, and when they jump, they change their position. So to keep hydrogen in confinement is something which is challenging, and ITER does it, as others, through what you may say is the Russian doll principle. Tritium is deep inside here, and any atom, any molecule which manages to move out of the inner doll is captured by the outer doll. So we have a kind of multi-layer concept for confinement of tritium, and we need to do that because we need to prevent, of course, spreading of radioactive material. We employ what is called a first confinement system to minimize tritium in accessible working areas, and a second confinement system to protect the environment. In reality, it looks like that. We have tritium in processing system. This is the first barrier here. We have a surrounding barrier, and this here comprises what is called the first confinement system. Well, unique in ITER, not done before in any other facility, is the second confinement system. So ITER has an additional feature, and this additional feature allows, through atmosphere deuteriation, through wind deuteriation, remove tritium and not sending it to stack if, in case, tritium manages to go out of the first barrier. In reality, it looks like that. This is a view inside of the tritium laboratory in Karlsruhe. You have glove boxes with the primary processing system inside, and as I said, not in this case, but in case for ITER, the building has also a confinement function, the secondary confinement function. Now, moving to the processing of deuterium and tritium in ITER, the closed loop. We have a storage of deuterium and tritium. We fuel it into the plasma. Burn-up fraction is low. Only a few percent of deuterium and tritium is fusing to helium. We have a processing system to remove helium and other off gases, go to isotope separation, and this closes the loop. There's more than 100 kilogram per year of tritium which requires to be processed in ITER during DT operation. At a price of $20,000 per gram, it means that the material we are processing is worth more than 1 billion euros. Good reason not to lose anything, besides, of course, the ecological reason. There is less than 2 kilograms of tritium per year being burned at any time. Well, at such a throughput, the loop, you may say, will not be 100% perfect. There is tritium which manages to move out, and this tritium is captured in what we call deuteriation systems. Another unique feature for ITER is that we, through water deuteriation and isotope separation, are able to recover this tritium as well and return it into the main cycle. So we put a lot of effort into the system design to make sure that all the tritium we have is used, is not being trapped or not being trapped or is escaping into the environment. So I would like now to give you a little bit more on the different areas shown here, and I would like to start with the fueling system. Fueling in ITER is through what is called pellet injection. There's gas puffing as well, but the major fueling once the plasma started is through pellet injection. How do we do that? Through what is called an extruder, two screws working inside of each other. Pellets of deuterium and tritium ice, frozen deuterium and tritium, are produced 6 by 6 millimeter in size, and then with compressed deuterium as a propellant, these pellets, with a kind of machine gun, are introduced into the plasma. You see here a pellet in the plasma of the Aztec's machine. Looks like a shooting star. The pellet speed is quite high, 1,300 kilometers per hour, which is faster than the speed of sound. There are up to 20 pellets per second. So that's the way pellet injection works. Solid tritium is introduced into the pellet. Machine itself looks like that. There is deuterium and tritium supply here. This is the pellet injector. There are valves. And here the pellets are sent to the vacuum chamber. Well, knowing the shape of the vacuum chamber, it's no surprise that these pellets go through bent tubes, like here and here, before they enter the plasma. So a very interesting technology which has been proven and is working well. From fueling to vacuum and exhaust processing. What is vacuum? Space not containing any real particle might be the answer of a philosopher or a physicist, which means there could be virtual particles in vacuum. 350 years ago, people did not know too much about it, and they referred to the fear of nature for emptiness. They had what is called the horror of vacuum. And Otto von Guericke, with his remarkable hemispheres, demonstrated that it's actually the atmospheric pressure which keeps the hemispheres together once they are evacuated. I've written down here the vacuum ranges low to outer space, very low. So nowadays there is no fear for vacuum anymore, but those who have seen the requirement for the vacuum in the ITER vacuum vessel, they now have some fear for the ITER vacuum handbook. And that's another story. The torus exhaust system is located below the diverter. There are pumping ducts, and at the end of these pumping ducts, cryopumps are being installed to pump all gases, the fusion ash, deuterium and tritium, from the plasma. As I said, you need to continuously remove helium together with the unburned DT, otherwise the plasma will not continue to burn. Eventually, plasma density control is through fueling and vacuum. There are cryo panels cooled down to very low temperatures, 4.5 Kelvin. You see such a cryo panel here. And in order to make it working, these cryo panels are covered with charcoal. Charcoal from coconuts. Not some coconuts. It was a certain product, a certain year, which turned out to be specifically good for this application. And because of that, there is, I don't know how many 100 kilograms being stored in Karlsruhe for ITER application. So we are well equipped as far as coconut charcoal for ITER is concerned. In reality, it looks like that. You see here a 50% half-scale model cryopump being installed, the valve partly opened, the pump being installed, and a rendered design of the pump. I will not go into detail here, but rather move on and give you some ideas about how isotope separation is being done. Well, if you are interested in grappa, then you may know that this is nothing but distillation of what is left when you produce wine. Alcohol as a less volatile component is in the is a distillate, and the residue is just thrown away. You drink the stuff here. Well, in order to produce a real good grappa, you would need to have this being done more than once, or in a multi-stage arrangement. You feed here, you get your grappa here, and you throw it away. You throw away whatever is coming out here. In ITER, it's just the other way around. The tritium is here, and the hydrogen comes up here. So we are interested in this case in the residue. It involves low temperatures because hydrogen isotopes are only liquid at about 20 K or minus 250 degrees centigrade. There's another feature. We have mixed molecules here which we need to split. And this is another challenge, or you may say an interesting detail. Last part is storage. Storage in ITER is through what is called a metal hydride. Certain metals have the property to dissolve hydrogen or to take up hydrogen even in an ordered structure. And in this way, I don't want to go into detail here, but rather have you seeing pictures to illustrate what happens. Imagine a sponge which takes up water. Like a sponge takes up water, metals take up hydrogen and this way act as an effective pump. Hydrogen is taken up into the metal, a very effective manner. Tritium pressure above the metal hydride at room temperature, very low, it's a very effective vacuum pump. If you heat the metal to 400 degrees C, the pressure is raised to 1 bar, and tritium can be withdrawn. Like, you cook water, and as long as there is water, as long as you provide heat, there is steam coming out. You cool the pot to room temperature, and the steam condenses, and this way the tritium is taken up again because the process is reversible. You see here the ITER design of a metal hydride container, benchtop size, not that big. There are different metals considered for this application. One ideal metal is uranium. Of course, it's a nuclear material. In this case here, it's of course being used because of its chemical properties, not because of its nuclear properties. But still, there is some concern. Transportation as a metal hydride, you see here somebody holding in his hand a container for 5 gram tritium, and to store 5 gram tritium, 130 gram of uranium is required. So after all, to house these systems, this is why we have the tritium plant, a building 80 meters long, 25 meters deep, 7 floors, 2 below grade, 5 above grade, full of equipment ventilation, of processing devices, pumps, as you would expect as you would expect it from a chemical plant. To come to the end of the talk, 2 slides about tritium in the environment. Of course, once there is tritium in the biosphere, either from nature or from human activities, if it's molecular, can be converted to tritium, to tritiated water, and once there is tritiated water, it can become organically bound. There is weakly bound material, weakly bound, organically available tritium in biomaterial, strongly bound in biomaterial, which is easily understandable, not exchangeable. The biological half-life of tritium in the human body is only 5 to 12 days. So even if you incorporate tritium, after 5 to 12 days, only half of that is left. Tritium can very easily be measured in liquids. The detection limit is very low. If you ask what is the impact of ITER to the environment because of tritium releases, then the answer is, well, because of the unique features of ITER, because of tritium removal through the deterioration system, because of removal and recovery of tritium from tritiated water, ITER will be well below the set dose limit. The set dose limit is 100 microsievert per year. ITER expects, on average, over the operational period, less than 10. And this needs to be compared with the natural background, which is 2000 microsieverts per year. Tritium content of surface water around here in Kalarash is typically 3 becquerel per kilogram, but it can vary depending on where you are in the northern hemisphere. To summarize, a fusion reactor requires a closed deuterium-tritium fuel cycle. Deuterium-tritium fusion is the technically most suitable fusion reaction. We need to remove continuously the helium ash because of the fact that only a few percent are burned in each cycle. Safe handling of tritium is achieved by multiple confinement strategies. And besides fusion, deuterium and tritium as hydrogen isotopes are materials which are subject to other applications in science and technology. With that, thank you very much for your